Top of the morning, afternoon, or evening, depending on when you're watching this video. We are at the point where we know how to calculate derivatives of different types of functions, and we're starting to look at applications of the derivative. Now, some of the most important applications in differential calculus are optimization problems in which we need to find the optimal or best way of doing something. For example, we might want to find the shape of a can that minimizes manufacturing costs, or minimizes surface area, or maximizes volume. We might want to find the maximum amount of acceleration of a space shuttle while it's taking off to know how much force the astronauts are going to be going through. We might also want to know the maximum attainable profit for selling a particular type of good, like an iPhone or a laptop or something like that. Now, these are all important problems to solve, and we're going to get to these types of problems, but they all involve finding a maximum or minimum value of a function, and I want to spend some time looking at definitions and examples. So let's start with a couple of definitions. Pew! Let C be a number in the domain D of a function f. Then f of C is the absolute maximum value of f on D if f of C is greater than or equal to f of x for all x in D. And similarly, f of C is the absolute minimum value of f on D if f of C is less than or equal to f of x for all x in D. Now, we have absolute maximum and absolute minimum here. We will sometimes just use the word max for maximum and min for minimum when we're too lazy to say or write 3 syllables, just want to shorten it. But let's think about this definition. So we've got some number that's in the domain of a function. So it's just an input value that we can plug into the function. And the function value there, we call it the absolute maximum on the domain if that function value is greater than or equal to all of the other function values on that domain. So it's basically the highest function value that we can attain. And similarly, for the absolute minimum, it is when we have the function value that is the lowest we can attain. It's less than or equal to all other function values. There is another name that we can say here. Instead of absolute maximum, we can also call this a global maximum or a global max. The same is true with a minimum. We can call it a global minimum. These are the same things. An absolute maximum is the same as a global maximum. Absolute minimum is the same as a global minimum. And in general, these all fall under the umbrella category of what we call extreme values. So if we're asked to find the extreme values of a function, that means we want to find the absolute maximum and the absolute minimum. It's an umbrella term that includes both of them. Now, I know we've just looked at several pieces of vocabulary all at once. They all have more or less the same meaning, but we haven't looked at an example yet. So let's take a look at an example, and I'm going to give you the graph of a function for us to look for the extreme values on. All right, so here is the graph of a function. It looks kind of like a polynomial almost, except we've got this sharp corner here that makes it definitely not a polynomial. And also, there's no arrowheads on the end of this curve, so the curve doesn't continue going up or down. This is the entirety of the function. You can think of it as having closed circles at the end, which is how I meant to be, but that didn't actually come through on the graph that I had copied and pasted. Anyway, so this is our function. This is the graph of y equals f of x for whatever the function is. And we want to talk about the absolute maximum value and the absolute minimum value. Let's start with the absolute minimum value. If you look at this graph, and we're looking for the point that has the smallest y value, the point that's furthest down on the bottom, we can see that it's going to happen right down here. And so what I'm going to do is I'm actually going to call this x value, I'm gonna call this, let's say e. Actually, let's name all of these values that look important. We've got a there. We've got b. If you're not sure why I'm picking values to be important, that will become clear later. I don't want to call this f because f is the name of the function, so I'm going to call it g. So these are just the x coordinates of the interesting parts of the graph. And we can see here that e is the x value that corresponds to this global minimum or absolute minimum. And the minimum is actually the function value there. So we don't say that the minimum is e. We would say that the absolute minimum is f of e. So it's the function value at e. It is that height. If we were to kind of draw that in, that height is f of e. I know that's a little small, not the best, but the absolute minimum or the global minimum is the function value at this point. It's the height of the function at that point. And then we could also talk about the absolute maximum. So again, if we look at this curve, we might ask ourselves, where does it reach the highest y value? And of course, that is at this end point over here at g. So we could say that the absolute max or maximum is the function value at g, so f of g. And in fact, that is what this distance is. This distance is f of g. That is the height. All right? So those are our extreme values. But they're not the only interesting parts of the graph. There are some other bits here, right? If we look at b, if we look at what's happening at the function around b, if we ignore what's happening over here and we're just kind of zooming in here, that looks kind of like a maximum, at least in that little neighborhood, in that little part of the graph, because it's going up and then it peaks there and goes down. Similarly, we could look at this point right here, the function value at c, and if we only zoomed in there, it would look kind of like a minimum just for that little region. And we do have names for these values. We call them local maximum and local minimum values. Boop. And here we have our definition of that. The number f of c is called a local maximum value of f if f of c is greater than or equal to f of x when x is near c. So if we're just looking nearby, I know that we don't actually have a maximum at c. This c is not corresponding to this c. This c just means a constant. But basically it says if we zoom in and we just look at a small area, then if the point is the highest point in that small area, if the function value is greater than or equal to all of the other function values nearby, that is a local maximum. And then similarly, we have a local minimum value if the function value is less than or equal to the other function values nearby. So if we want to look at some of the interesting points here where we have local maximum and local minimum values, we already talked about what happens at b. That is going to be a local maximum. So we have a local max of f of b, the function value of b. And sometimes we want to say where that occurs. So we might want to say it occurs at B. Now, obviously, f of b is occurring at b, but sometimes if we're actually looking at an example where we have numerical values, if the height here was 7 and the value of b was 1, we might say, oh, we have a local maximum value of 7 that occurs when x equals 1. So it's a good idea to say where these local maximum and minimum values occur. Sometimes we'll be asked for that. All right, so that is a local maximum. Are there any more local maximum values? Looks like there is here at D. So we could also say we have a local max of f of D. That is the local maximum value, and of course it occurs at D. We also have 2 local minimum values in the middle of that function. We have this one right here. At C, we have a local minimum. And also at E, it is the absolute minimum, but we could also refer to it as a local minimum if we want. So we have a local min of f of C at C and a local min of f of E at E. One question you might have, what about the endpoints? If we look at A, is that considered a local minimum? It is, the function value is smaller than any of the other function values nearby, but it's not defined on one side. So the question is, do we count that or not? And the answer is actually ambiguous. Some textbooks include endpoints as local maximum and minimum values. Some of them don't include endpoints. And as I record this video, we're currently considering changing textbooks. So I don't want to say, oh, our textbooks does this, because that might change if the book changes. So please feel free to look at the book. If I'm teaching a course in person, I will explain in person whether or not we're going to include those as local maximum and local minimums. If I'm teaching online, I will put things in the online system that explain that. But because the last book we used did not include those as local maximum and minimum values, that's probably what my default is going to be as I record these videos. But again, different books use different definitions.